All right, y'all. We are at the end of our introduction to equilibrium. The ideas that we've talked about here, we are going to apply in units 9, 10, and 11, and we will be kind of off to the races with these. But this is probably, I think, the most important part that you take away from all these. So I know I spent a ton of time doing Le Chatelier examples. This, though, you really need to have down pat. So we will be spending a lot of time kind of talking about this, and they are ice tables and how they apply to equilibrium. So here's the deal. You generally can't do stoichiometry when we're dealing with an equilibrium problem. If we allow a chemical reaction to run for some amount of time, like give it, minutes or whatever for it to do its thing, eventually, if it's a reversible process, it will come to an equilibrium. But equilibrium does not mean, hopefully you've picked this up, that our concentrations are equal or that we have all product or we have no product and all reactants. It's just kind of a mess. And so when we do equilibrium calculations, we have to take that into account. I can't just say all my reactant turn to product and I'm going to do stoichiometry. The math that we do depends on starting amounts that you have. It depends on your equilibrium constant, how far that is product or reactant favored, and then even the coefficients of our balanced equation. And so to kind of organize our life and deal with all of this, what we do is we use something called an ICE table. Now, an ICE table is just an organizer to help us keep track of all of our math processes, and then we deal with the equilibrium expression. So here's how an ICE table is generally set up. Some people call them RICE tables as well. And the ICE stands for the starting letters here in our first column, and the R would be the R in RICE. So when an ICE table is set up, what you do is you put the reaction you are dealing with, the equilibrium reaction, up at the top here. Make sure you put it in the coefficients and everything is balanced correctly. Now, when you read through your problem, you are probably going to be given some pieces of information that can fill in this table. I stands for the initial concentrations of those substances. So whatever your starting molarities or pressures would be, if you were given pressures, would go in this box. Now, this is, the C stands for change. You can see me kind of waffling back and forth here. So more often than not, what happens is you are given all reactants and nothing with your products. And I would say that the majority of the time when we are applying those things, that's how it's going to be. So what will happen more often than not is that you are going to see a change in concentration where the concentration of my reactants goes down. And that depends on the coefficient in front. So if you think about the concentration of A, whatever that's going to be, it'll go down by some factor X as time progresses. But B's concentration, because there's a coefficient of 2, is going to go down by twice that much. Okay? And then C, in turn, is going to go up by X because there's a coefficient of 1 here. If there would have been a 3 here, it would go up by a factor of 3. And this kind of ties into our reaction rates that we talked about too, how those coefficients play into that. Now, my equilibrium concentrations, the E in the ICE table, that is the initial box plus the change box. So whatever those things would be, it would be like 1 minus X or 2 minus 2X, or sometimes, a lot of times actually, this C concentration is 0, and then it would be nothing plus X. And so what you would do then is you take these two boxes and combine them to get these equilibrium concentrations. And then to solve, you put them into your equilibrium expression and go from there. Now, that looks crazy, and it will make more sense when I do an example. So you can expect example number 1 here. Even at a high temperature, the formation of NO is not favored. So we get our reaction here. We get our K value. In this case, Kp, woohoo, pressure time, is going to be very tiny at 2,000 degrees Celsius. What is the pressure of NO when a mixture of 0.2 atmospheres of N2 and 0.15 atmospheres of O2 reach equilibrium in a container? Now, when you think about this, normally we would just do a limiting reaction problem, right? We'd figure out how many moles of product we got, do the math, and it would be good to go. But this is a KP issue because pressure here, or KP value, is very small, which means that we aren't going to get a lot of product made. So what we need to do is kind of organize ourselves and figure that out. So thus we begin our ice table journey. Okay, so when I start this off, the first thing that I like to do is I like to write my reaction and get that all set up. Okay, and then I literally put ICE, initial, change, and equilibrium. So these are pressures. So we're going to put in pressures here instead. So our initial pressure of N2 is 0.2 atmospheres. Now you could put the pressures in for units here, but I don't really think it's important until we are dealing with the end unit, because the K value, even if it has a KP, isn't anything with units. So our pressure of our N2, or N2, yes, is 0.2. Pressure of our O2 is 0.15. Okay. Now it is not telling me anything about the NO, so I'm going to assume it is 0 to start off with here, which means that our reaction has to make some products here because we don't have any. So what's going to happen is my N2's concentration is going to go down by a factor of X. My O2 will go down by that same amount because I have coefficients of 1 here. And my concentration, or my pressure of NO, is going to go up by a factor of 2x. So my equilibrium value is going to be 0.2 minus x, 0.15 minus x, and 2x. Okay, so hopefully that makes sense so far. All of these values then are going to be put into our KP expression. So in this case, my KP expression is equal to the pressure of my products, which is NO, and I'm going to square that because of this coefficient here of 2. And then that's going to be divided by my pressure of N2 times my pressure of O2. So it's just like a regular K expression, but all I'm doing is putting in the pressures. And then what we do is we put in these values into our expression. So it's going to be 2x squared over 0.2 minus x times 0.15 minus x. And then we set all of that equal to our equilibrium constant, which is 4.1 times 10 to the negative fifth. And now if you look at this, we want to solve for x. So when you're looking at this, you should realize that we've got a quadratic equation situation. And honestly, that is a huge pain in the butt. So here's a fun little trick that you can do. If we can avoid the quadratic equation situation, that would be real great. So here's a trick. This K value here is very, very small. It means not a lot of product is going to be going away. What that also means is that if we look at this X value honestly is so teeny tiny that if I just got rid of this, it probably wouldn't make that big of a difference. So we're going to take this dog out for a walk here and see if we get anything crazy. So this whole thing is equal to 4x squared divided by 0.03. That's just doing this math here, collecting all these terms. Okay. So what I want us to do is I want us to solve for x to see if this term is something that we can ignore. If it is something we can ignore, our life is just dandy and we can not worry about that. Otherwise, we got to go back and we got to solve using the quadratic, and that makes me sad. So let's do the math here. I'm going to rewrite this over here because it's kind of icky. So 4.1 times 10 to the negative fifth is equal to 4x squared over 0.03. Now, if I want to get 4x squared by itself, I'm going to bring the 0.03 up on both sides. And that gives me 1.23 times 10 to the negative 6 equaling 4x squared. Okay. If I do the math and get x squared by itself, I've got x squared equaling 3.08 times 10 to the negative 7th. I'm doing that math because I assume you can do that in your head. And then if I solve for x, my x comes out to be 5.55 times 10 to the negative 4th. Now, because x is a pressure value, the units all of a sudden pop out as pressure. If this were a molarity problem or a concentration, we would be solving a capital M here. So this is equal to my pressure change. So if we go back to my ICE table here, it's going to be my new pressure 0.2 minus 0.55 or 5.55 times 10 to the negative 4th, which is really small. Now, how do we know if this is negligible enough? There is something called the 5% rule. Okay, the 5% rule that we can go through. And the 5% rule tells me that if X is less than 5% of my original amount, this 0.2, I can ignore it and it's a totally legit thing. You ask yourself, how can you do that? That K value here has a 5% error. So if this number is within the 5% error, we are golden. So it's going to be 5.55 times 10 to the negative 4th divided by 0.2 and multiplied by 100. So if we look at that, we do the math, we end up getting a percentage of 0.28%, which is well under 5. So that is a safe assumption. And I can tell you on the AP exam, you're probably going to be able to do that. Okay. So we didn't even answer the dumb question yet because the question was, what is the pressure of NO in the container? Okay. So NO's pressure in the container here is going to be 2 times our X value. So our pressure of our NO is equal to 2 times that 5.5 times 10 to the negative 4th atmospheres. So the pressure is going to be 0.00111 ATMs. If you think about it, because our K value is incredibly small, we have this teeny tiny K value, it makes sense that we are not going to have a high pressure of our product because of that. Okay. So this is just kind of the very basics of how to set up your ICE table. We will go into more detail when we get into class on how to use this if we're given other information, but this is just kind of the bare bones setup of how we do this. So the change is always equal to the coefficients, and then we plug the values in here. Once we get into class, we are going to be talking about what if I get this information? Can I kind of backtrack and figure stuff out? So hopefully this clears things up. If you have any questions, please let me know. Otherwise, good luck.